Hello, guys. So today we'll learn how to induct, how to four ways to prove Euler's theorem. So what is Euler's theorem? Euler's theorem is basically a complex analysis equation that helps you, helps it helps our math in a lot of ways. It's basically e to the ix power equals to cos x plus I sine x. So without further ado, let's jump into it. So our first method to prove this thing is to use derivative properties. So let's first consider a function f t equals to e to the negative it power times cos t plus I sine t. So this is defined for all t in real numbers set. So by the product rule of derivatives, we have f prime t equals to e to the negative it times I cos t minus sine t minus I e to the negative it cos t plus I sine t. So for people who's not familiar with product rule is just when you're calculating the derivative of product of two functions, you multiply the derivative of the first times the second function plus the first function times the derivative of the second function. So basically so what does that mean? What does f prime t equals 0 mean? It means that it's identical for all t in real numbers. Hence, f is constant everywhere. And since f0, so f0, if we plug into it, f0 equals to e to the 0 times cos 0 plus I sine 0. Sine 0 is basically 0. So cos 0 is 1. So we have f0 equals to 1. So what does that mean? F prime t equals to 0 implies that it's constant. So we have it equals to ft equals to 1 for all t in real numbers. So we now have that e to the it cos t plus I sine t equals to 1 for all t in real numbers. So we basically just time e to the negative it to the right, so we get e to the it equals to cos t plus I sine t. So our first method is done. And our second method is going to be using Maclaurin series. So Maclaurin series is like this. Sine x equals the sum n equals to 0 to infinity, negative 1 to the nth power divided by 2n plus 1 factorial x to the 2n plus 1 power. So let's list a few items to see what it looks like. X minus x to the third power divided by 3 factorial plus x to the fifth power divided by fifth factorial, and so on. So let's just put dots. And cos x is equals to n equals to 0 sum to infinity, negative 1 to the nth power, 2n factorial, x to the 2nth power equal, let's just list a few items. 1 minus x to the second power divided by 2 factorial plus x to the fourth power divided by 4 factorial, and so on. So what about e to the z? Well, we use z to refer to a complex number. So it equals to n equals to 0 to infinity sum z to the nth power divided by and factorial, and this equals to 1 plus z to the second power divided by 2 factorial, and so on. So we now substitute z equals to ix in the last equation, and let's see what we get. E to the ix equals the sum n to the n equals to 0 to infinity ix to the nth power divided by n factorial equals to 1 plus ix plus ix to the second power 2 factorial plus ix to the third power divided by 3 factorial plus so on. So when we expand all that and divide these polynomials into two different parentheses, we get 1 minus x to the second power divided by 2 factorial plus x to the fourth power divided by 4 factorial plus so on. And we also get on the other side I times x minus x to the third power divided by 3 factorial plus x to the fifth power divided by 5 factorial, and so on. So we basically have cos. So by our Maclaurin series, the left side is cos x, and the left side is I sine x. So basically we just proved the Euler's theorem. So let's look at our third way to prove this thing. And this way was by simple complex analysis, and it is used by Bernoulli. So and it actually led to the first proof of Euler's theorem. So let's 2i divided by x squared plus 1 equals to x minus I 1 over x minus 1 minus 1 over x plus I. So we basically just use these fraction tricks, and we'll discover that they're equal. So we'll not talk over about it. So now we integrate the both sides just you would integrate real valued function of this form. So integral 1 over x squared plus 1 is arctan x. So we get 2i arctan x plus c equals log. Notice that this is of base e. So we also get on the other side x minus I divided by x plus I, which will further replace x with tan y divided by 2. So we'll discover that 2i times arctan tan y divided by 2, which will cancel. So we basically are just left with iy equals to log tan y divided by 2 minus I divided by tan y divided by 2 plus I. And we can do some we time both sides of the fraction with cos y divided by 2, so we'll get sine y. So log first, sine y divided by 2 minus I cos y divided by 2, and sine y divided by 2 plus I cos y divided by 2. And we also have iy on the other side. So if we exponentiate the both sides, which means use e and exponentiate this e thing with both sides of the equation, and we'll get e to the I. Oh, let me see. Oh, we still have c left. Sorry, I made a mistake here. So we have c. So plus c. And so we'll get e to the iy, and we'll make an abbreviation to make this expression simpler. We'll just use the same c to represent e to the cth power. So we'll have c times e to the iy equals sine y divided by 2 minus I cos y divided by 2 divided by sine y divided by 2 plus I cos y divided by 2. So we simplify the expression on the right side by timing the denominator with its conjugated form. So we'll get sine y divided by 2 plus cos y divided by 2, sine y divided by 2 squared plus cos y divided by 2 squared, with sine y divided by 2 minus I cos y divided by 2 squared on the numerator. So finally, so we notice that sine x squared plus cos x squared is just 1. So we'll only have the numerator left. So we'll have equals to y divided by 2 minus I cos y divided by 2 squared. And this, in fact, equals negative cos. This, in fact, equals negative cos y minus I sine y. Is that so? Yeah. So we have here c e to the iy equals to negative cos y minus I sine y. So if we substitute y equals to 0, so we'll get c times e to the 0 equals to negative cos 0 minus I sine 0 here. So we'll get c equals to negative 1. So therefore, we have e to the iy equals to cos sine y plus I sine y. So we have our last way of proving Euler's equation. So it's by using the limit definition of e to the x. So e to the x equals the lim n to infinity 1 plus x divided by n to the n squared, nth power. So then we have e to the ix equals the lim by simple deduction plus 1 plus ix divided by n to the nth squared. So by putting 1 plus ix divided by n to polar form for complex numbers, we realize that it is derivative 1 plus x squared divided by n squared, which is basically the modulus of the complex number. So we also have sine the incident angle plus I cosine cosine the incident angle, which is arctan x divided by n, since x over n divided by 1 is x divided by n. So we also have plus I sine arc tan x over n. So by De Moivre's formula, we have 1 plus ix over n to the n squared equals to 1 plus x squared divided by n squared to the n divided by 2 power cosine n arc tan x divided by 2 plus I sine n arc tan x divided by n. So basically we just time the angle in sine cosine function and sine function by n and power the constant multiplied outside of it by n, raise it to the nth power. So we then have we now have, since this thing is we take n to infinity, so it's like we take n to the infinity on the left side, and we also take n to the infinity on right side. So we now realize that limit n to the infinity 1 plus x squared divided by n squared to the n divided by 2 power equals to 1. And how to prove that? So we have limit n divided by so this thing is equals to 1 plus x squared over n squared to the n squared power, and then to n to 2 over n power. And we realize this thing, we recognize that the limit below is just another form of e to the x power. So we'll have that e to the x squared. So this thing is equals to e to the x squared. Then we still have the limit here, n to the infinity, e to the x squared, and then 2 divided by nth power. So now since any constant bigger than 1 or equal to 1, let's just because 2 over n tend to 0 when n tends to infinity, we have this thing is equals to e to the x squared to 0th power. So we basically just have 1 left. So we now have officially we have another limit here, which is limit n to the infinity n arc tan x divided by n, and we claim it to equal to x. And now we'll prove why. So if we put h equals to x over n, so we'll have that the thing above is equals to x arc tan h divided by h. And this thing, since arctan 0 is 0, we'll have this, it's equals to this thing, arctan 0 divided by h. And we recognize that if h tends to 0, this is actually directly the definition of the derivative. So we let h tends to 0, which since h equals to x divided by n, when n tends to infinity, h just tends to 0. So let n tends to infinity. Now h tends to 0, and we now have this the expression above the limit is equals to x times arctan 0. Oh, now the derivative is defined at 0, and we let h tends to 0. So we now have arctan 0 prime derivative. Prime means derivative, right? So we now have x left. So by plugging in these two limit, it results into our into this thing eats 1 plus I x divided by n to the n squared equals to 1 plus x squared over n squared to the n divided by 2 square power times cosine n arctan x divided by 2 plus I sine and arctan x divided by 2. So we now have that. So we now have e to the ix, which is the left side, equals to 1, 1, 1. Since we just resulted in this limit expression when n to the tends to the infinity equals to 1, and the thing inside cosine function and sine function results to x. So we have e to the ix equals to 1 times, let's just remove 1, so cosine x plus I sine x, which is our last way of proving this Euler's theorem. So I guess this is the end of today's video. Thank you.